Okay, good morning, everybody. So we continue today our adventure with path algebras. Well, the previous lecture was devoted into defining path algebras and understanding what they can possibly be. Today, we're going to focus on what path algebras cannot be. All right, so this is like examples and counterexamples. And in order to make this analysis, I need to recall some basic notions from the previous semesters. Namely, I need to define a connected graph. And to this end, first, I need to define a finite undirected path. And of course, it just vanished. It's a bit whimsical. Yes, here it is. Okay, so let's take any graph. So what is a finite undirected path? Well, of course, it can always be a vertex or a finite sequence of edges. But now, instead of satisfying one relation that the end of the former edge is the beginning of the next edge, now we have four different possibilities. They're highlighted here on the picture. They can agree by having the same big, what's happening? I'm not doing anything and it jumps out. Sorry. I mean, this is our future. Artificial intelligence, matrix, computers will do whatever they want without us steering them. So now you see on the picture, we have four possibilities. The two consecutive edges can meet at the beginnings. They can meet at the ends, or it can be again that like it was in the directed path, that the end of one edge is the beginning of another one. But now you also have two possibilities. They can go left to right or right to left. So this is why this condition for a sequence of edges being a finite undirected path, well, has four possibilities. I think it's very intuitive. We don't need to linger on. And now this allows us to define, connected graphs. I went too much down? Yeah. I jump pages without wishing to do so. That's really disturbing. Okay, so this I highlight. I want to highlight this definition. Okay. Sure. But it's just the end. This is the last part, and I'm switching to writing. So you can teach me during the break. This is really frustrating. I don't understand why it misbehaves like this. Okay, so first, for starters, I want to unhighlight it. How do I do it? Trash. Perfect. And now I want to highlight this definition. Perfect. Okay, so say that the graph is connected if for any pair of two different vertices, there exists a finite undirected path between V and W, which means that this path has at one edge V and at one end V and another end W. And again, you have a number of possibilities because V can be either the beginning or the end of the first edge. And then W can be the end or the beginning of the last edge. Okay, so again, you have four possibilities, but it's very intuitive. So I now can quit this horrible Acrobat reader who misbehaves, doesn't like me, and we will go to writing on screen. But this was really necessary to recall what a directed graph is. Connected graph is, because it will be now first. I will need it for my own theorem and also for a recitation class. Today we have two theorems about connected graphs. So it's very good. It's very important that all of you have it clearly in your mind of what we mean by connected graphs. So this is a very natural combinatorial definition. Now I go back to Zoom. What I already joined the meeting. I didn't understand it. Meeting controls, yes. So I stop sharing and now I start sharing again, but now my whiteboard. Okay. Full screen. Controls down. this controls also down, please. Yep, this is what we choose. This is what we have. Okay, so for starters, let me give you a certain general definition. It's pretty obvious, but it's important. If you take, I'm going to define what we mean by a graded algebra, okay? So this is a certain elementary definition. So let gamma be any monoid. Doesn't have to be a group. It might be a group, doesn't have to be. And A be any algebra. Now we say that A is gamma graded. When the following condition is satisfied, I can write it down as a vector space as a direct sum over all gammas in gamma of A gammas, and this is a crucial condition, compatibility with a monoid structure. A gamma times A gamma prime is contained in A gamma times gamma prime. Okay, so first I have a vector space decomposition of my algebra A into the direct sums of A gammas. And these A gammas are compatible with a monoid structure in the sense which I wrote right in here. And this is called gamma grading. We don't need it for the time being, but I cannot resist telling you, like Oscar Wilde, I can resist everything except for temptations. So I want to tell you what it means that we are strongly graded. So for people who work with non-commutative principal bundles like Sophie, for instance, that's important. And it turns out that when our Hopf algebra is just a group algebra of a discrete group, then the coaction of such a Hopf algebra is free if and only if your algebra is strongly graded. And strongly graded, so just let me write it down. It's not in the notes because we don't need it for our lecture, but I think it's good to know. And I have space here. So, and A is a gamma graded algebra A is called strongly gamma graded. Whenever here, instead of inclusion, we have equality. So A gamma gamma prime, in fact, equals A gamma prime. Okay. And I like this word strongly because, in fact, when you're doing a Hopf-Galois theory, you see, you know that your extension is Hopf-Galois, Galois condition is satisfied if and only there exists a strong connection. So the strongness, and this is also if and only if you have some strongly monoidal functor. So that this strongness is somehow tantamount to freeness of actions when you in the non-commutative world. Okay, but just purely algebraically for the time being, what you need to remember is what it means that we have something gamma graded by a monoid. And by the way, you might also bear in mind that strong gamma grading is not a big deal. It just means that instead of inclusion, you have equality. Okay, but this equality is tough. I mean, it's not so easy to prove it. Usually the containment is easy. I mean, by the very construction, you define your spaces in such a way that it's obvious that you have such a containment. But equality, that's quite a different matter. Okay. Now that we know what it means that an algebra is gamma graded, it makes sense for me to write that the path algebra KE for any graph E is n graded, where n are natural numbers. We agree that natural numbers form a monoid. For me, 0 is always a natural number. You know, it's like the difference between Europe and the United States. In America, you don't have a ground floor. It's always first floor and second floor and so on. There's no 0, there's no ground floor. So natural numbers start from 1. In Europe, we always have ground floor, floor number 0. So I have European attitude to natural numbers. We start from 0. Okay, so path algebra KE is n graded, and now we know what it means. But how is it n graded? Of course, it's n graded by the lengths Uh-oh, I forgot to switch off my phone. I mean, if you have that question, ask it on Zoom, don't call me now. Well, as a professor of mathematics, I could take this call, talk to him, but let me just mute my phone. But once it happened to me, and I thought it was very embarrassing. I had a lecturer who, in the middle of a lecture at the blackboard, he received a phone call and he actually answered it. And he was speaking to a plumber. I thought it was very embarrassing to speak to a plumber in front of a class we are teaching, but people are different. So I apologize for forgetting to switch off my phone, but now it's done, it's muted, nobody will disturb us again. Okay, well, I think it's pretty obvious. We can simply write KE as KE0 plus KE1 plus KEN, and so on and so forth. Where here, by this index, I mean that I take the linear span of paths of length n, okay? So this makes perfect sense, and obviously every path has its length, starting from 0 to arbitrary natural number, and this is how we can do it. And I want you to note, we will use it on and on in today's lecture, that if you take just the positive paths, and you can denote it like this, KE with E bigger than 0, this is so-called arrow ideal. The arrow ideal. Okay. So you always have this natural decomposition of any path algebra into the commutative part. These are just finitely supported functions on vertices, KE0, yeah, the linear span of paths of length 0 of vertices. And then you have paths that are of positive length. So they are made out of edges, out of arrows. This is why it is called the arrow ideal. So you might note that, and we will use it in about a second, that any non-commutative path algebra is never simple. Yeah, because in order to have your path algebra non-commutative, you must have at least one edge, but when you have one edge, you have a proper ideal, okay? And this will help us to determine that, for instance, path algebras cannot be matrix algebras. That's what I want to convince you of today. Okay, so, well, also clearly you can see that if you take KE and divide it by the arrow ideal, you'll just get the commutative part, KE0 of all finitely supported functions from the set of vertices to a base field K. All right. And well, you can immediately infer what I just told you, but I think it's worth writing it down. I write it as a proposition because it's an important statement, although it has no proof because it's obvious. So the path algebra KE, but it's good to have a formal statement. the path algebra KE is simple which, let me remind you, means that the only ideals are 0 and the whole algebra, if and only if E has no edges and at most one vertex. E has no edges and at most one vertex. So in other words, unless your path algebra is 0 for the empty graph, or just the ground field for the beautiful graph consisting of one vertex and no edges, then this is not simple, okay? And this allows us to have an immediate corollary. The matrix algebra M and K with n greater or equal than 2 cannot be isomorphic to the path algebra of any graph. Well, the proof is immediate because MNK is simple. This will be an exercise. It's a beautiful exercise, okay? It has no proper ideals. It's simple and non-commutative. And KE non-commutative is never simple. Right, so there cannot be an isomorphism between one algebra which is simple, one algebra which is not simple. Okay, I skip writing the full English words, just the whole proof is based on the simple observation, right? That matrix algebras are simple non-commutative for n bigger or equal to 2, and all non-commutative path algebras are not simple. Good. Okay, go to the next page. So this was a warm-up. Okay, this was easy peasy. And now I would like to prove something more substantial. Namely, I would like to convince you that not only a path algebra cannot be a matrix algebra, it cannot be a direct sum of full matrix algebras. And that's more difficult. And this requires a certain particular theorem, which will take me at least half an hour to prove. That's a theorem I advertised a week ago. I like it quite a bit, but please be careful and verify the proof with me, okay? So let's do it. This is the first non-trivial theorem result of the semester. And let's do it carefully. But the statement first. So the path algebra KE decomposes into a direct sum of non-zero subalgebras A1 and A2 Well, which means I can write it as a direct sum, and A1 times A2 is 0. So this is decomposition as algebras. Not in the grading, this decomposition, the direct sum was in the sense of vector spaces, right? I never told you that A gamma prime is 0 for gamma different from gamma prime. Quite the contrary, I told you that it's contained in A gamma prime, and if it's strongly graded, it's actually equal. So it's a different story, okay? Grading and decomposition into direct sums are completely different. Here, I mean this decomposition in the sense of algebra. So in particular, we multiply component-wise. So A1 times A2 is 0, okay? And the claim is that this is if and only if E is a disjoint union. Maybe I'll write it in symbols. What? This is a disjoint union of E1 and E2. So E1 and E2 are subgraphs, and they are non-empty. And of course, by disjoint union, I mean that these graphs intersect to 0. And they are such that as you can guess, the path algebra of E1 is equal to A1, and the path algebra of E2 is equal to A2. Okay, so this is a very strong theorem. Here you say that you can decompose your path algebra into smaller pieces in the sense of direct sum, and this is tantamount to decomposing your graph into disjoint non-trivial pieces, okay? And one direction is easy, is relatively obvious, right to left, or if you want, down to up. If my graph is disjoint, if it's disconnected, it's obvious that when I take the path algebra of such a disconnected disjoint union of subgraphs, I will get a direct sum of algebras. This is not a big deal. It's just one paragraph of baby checking. But the other way around, that's something which will require quite a bit of work. And for instance, it definitely doesn't work for Leavitt path algebras. Yeah. So the claim one way is true for anything. Path algebras, cone algebras, Leavitt path algebras, graph system algebras, you name it. Okay, but if you want to have the opposite implication, this is a particular feature of path algebras. Okay, so let's prove it. Oops, but we prove it with something that writes, not that erases. Proof, and I'll start with this difficult part. Okay, so the implication left to right. So now assume that indeed our path algebra KE decomposes into A1 plus A2, and they are non-zero. Okay. I want to define a certain auxiliary object, which is fundamental in our argument. I want to define Pi in the following way. These are all finite paths in my graph E that have a property that chi Pi, so the sort of Pi characteristic function, is in AI. And of course, I take my I to be 1 or 2. Okay, this is just a definition. For all we know, it might be empty. We don't know. But I can make such a definition. What I want to prove is that, in fact, P1 and P2 are disjoint, and their union gives us all paths. So I have the composition of a space of finite paths into P1 and P2. Okay. Oh, thank you. Thank you, of course. Of course, yes, thank you. But please watch out, because this is a brand new proof. So I would like it to weed it out. Yes, chi p, and in the notes is written chi p. Yeah, thank you. Okay. So Now we take chi p, and because ke is this direct sum of a1 and a2, of course we can uniquely decompose it into a1 plus a2, where ai is in ai, for I equal 1 and 2. And this decomposition is unique, of course, because this is a direct sum decomposition, okay? But then, remember, not only it's unique, but we have that A1 times A2 equals 0. So this is a fundamental property we are going to use, okay? Because I have this decomposition as algebras. KE equals A1 plus A2 as algebras. So we multiply component-wise. Okay. And how do we do it? Well, A1 and A2 are in our path algebra KE. So if I take all finite paths, it will give me a basis, so I can decompose them. And there is some finite linear combination of chi q's that will give me A1 and that will give me A2. But remember that A1 plus A2 is equal to chi p. And whatever I have with my coefficients for A1 and A2, at the end of the day, when I sum it up, all coefficients next to chi q, where q is different from p, must vanish. And the coefficients next to chi p must add up to 1, because chi p is the basis element, okay? So this means that I can write down A1 as a sum, finite sum, of course, over q, well, which is at finite path, but not p. And I'll write my coefficients alpha q and chi q. And here I distinguish, I have also some alpha p times chi p. But then, so that this adds up to, so right now this is arbitrary, okay? This is arbitrary, I just split my finite sum into 2 pieces, so chi p is distinguished. But now in order to have equality chi p equals A1 plus A2, I know my coefficients for A2. I know that I have to write it down as the same kind of a sum over q's, different from p. And here I have to have minus alpha q, chi q. And here I have to have plus 1 minus alpha p, chi p. Right? I think this is clear. Yeah, I wrote it here FPE. Just remember that these sums are finite. In the notes, I wrote that it belongs to F, where F is a finite subset of FPE. Okay, and this is because, let me make it explicit. If I take all these guys, all chi R's with R running FPE, this is a basis by construction of KE. All right, now let's consider a special case for a while when P is a vertex. So assume for a while that P is a vertex. I mean, it is a finite path. But then A1, A2 equals 0 implies that alpha p is equal to 0 or alpha p is equal to 1, because V cannot be an element of the following set. I take V times, okay, I must correct it. So here, this is, I did it for a reason. So this is a finite set. K not containing P, and likewise here. This is the same finite set not containing P. Let me not write it. F is a finite subset of the set of all finite paths. Okay, so V is not an element of the following set. I have V on the left times F minus V union with F minus V times V on the right. Okay, let's see why is it obvious. Why do we have such an argument? Yeah, I mean, I have right. I multiply A1 times A2. Okay, and then let's see what happens when I multiply these two chi p's. So now chi p is chi v, and remember this is an idempotent. So I will have alpha p times 1 minus alpha p times chi v squared, but this is just alpha p times 1 minus alpha p chi v, which is still a basis element. And we cannot produce chi v out of any other chi q's. Why? Because if I multiply v times the set of finite paths not containing v, then if I hit another vertex, I will have 0. Right? This will not give me this will not form a path. And if I hit some edge or a path where it will not give me 0, well, it will be something of length positive, of a positive length, so it will not be a vertex. Okay, and the same when I do it from the other side. And when I multiply sets, well, maybe I should also write a union with F minus V squared. Okay, and when I multiply q's from F minus V set, well, then again I will have, in order to get a vertex, I have to multiply vertices, and the only way to have chi v as a result of multiplication of two chi v primes is when chi v prime is equal to chi v. Okay, because they are mutually orthogonal idempotents. Yeah, we always have to remember this is from path algebras. Chi v prime is delta v prime chi v. Okay. So if I multiply with positive length paths, of course I stay in positive length paths, so I will not get a vertex. So the only hope to get chi v from other parts of a multiplication would be to multiply vertices, but the only way I can write chi v as multiplication of some other chi's would be when the other chi's are just chi v. So that's the only way to write chi v as a result of multiplication. That's the only way. And of course, we cannot do it in this set, because this set by assumption does not contain v twice. It's either not there at all, or it's only on one side. Okay, so an expression chi v times chi v will never appear when I multiply anything else but these two elements. Okay, and we are in the field. There are no zero divisors. Chi v is a basis element, so we must have that alpha p times 1 minus alpha p is equal to 0. So it means that one of them is equal to 0. And this is what I wrote: alpha p is 0 or alpha p is 1. Okay. Everybody happy? Yeah, do you agree, Tanya? Okay. Good. Now, next. I claim that chi, well, because chi v is not idempotent. So you agree that I can write it as chi v, A1 chi v plus chi v, A2 chi v. Right, this is obvious because chi v cubed is chi v, so I can put chi v from the left and the right, and therefore I have also the composition into chi v A1 chi v plus chi v A2 chi v. All right, and remember, because this is a direct product algebra, in fact, these subalgebras A1 and A2 are two-sided ideals. Okay, they are not just subalgebras; they're ideals. So this means that this is again in A1, and this is again in A2. But this is a direct sum decomposition, so this must be unique. So it is unique, and therefore we can conclude that chi v A1 chi v is equal to A1, and chi v A2 chi v is equal to A2 because of the uniqueness of such a decomposition. Yeah. Maybe I'll write it down, due to the uniqueness of the decomposition. Of A as A1 plus A2 with AI in AI, I want to. Okay. But now I can conclude that all Q's in this F, so let me, okay, it's a certain shortcut. If I want to say that this finite set has such property that all coefficients that appear next to basis elements indexed by this finite sets are non-zero, then you see that you only care about loops that are based at V. Okay, let me write it down. So hence, if I take Q in this F less P, they are loops based at V. Right, because otherwise chi v hitting left on right will annihilate. Okay, and because we have this equality and we have a uniqueness of writing any element in terms of basis elements, so coefficients must be equal next to basis elements, we conclude that indeed because of these equalities, the only thing which can be non-zero is whenever my path Q is a loop based at V. It must begin at V because I multiply with chi V on the left, and it must end with V because I multiply with chi V on the right. So it has no choice. If it is survive this sandwiching between chi V's, then it must be a loop based at V. Okay. So coefficients next to any other chi Q's must be zero, so we might as well forget them and say that our sum is only over Q's that are loops based at V and that are different from P. Okay. Now, it follows that alpha Q's are equal to 0 for all. Let me write it down and then see why it is true. I simply forgot some arguments. Okay, so alpha is 0 for all Q in the set F plus P that are edges because there are no edges in this set squared. Now, why did I? To be honest, I don't understand what I just wrote. You see, this is a proof I did a week ago, not last night. And I forgot why. Why does it follow? Okay, so I know that there must be loops based at V. Why do we have it? We established that three are loops based at V. And why they cannot be edges? Or if you want loops of length 1. Okay, I think we still have that this, okay, if I multiply A1 times A2, I must have 0. Okay, so why does it? I think this is related to, we need more space. I think this is related to the fact that now remember that, we know that alpha V is equal to 0 or alpha V is equal to 1. This we established, okay? So this means that either we have A1 is the sum over these loops that are different from P, and by the way, they must be loops. They cannot be vertices because vertex chi V is excluded from this sum. I mean, remember P is equal V. Maybe I should write it down. Okay, like this. And if I have any other vertex, of course, it will be annihilated by chi V. So these are indeed these chi Qs. I mean, Q is definitely a loop based in V. And then either we have that's it because we have alpha V equal to 0, or A2 is equal to such a sum. Right, chi V is only on one side. So basically this means that, what does it mean? Why did I write this sentence? I honestly don't understand it. I don't understand my own proof. And we still have that chi V is equal to A1 plus A2. Well, so one of them is equal to 0. No, wrong. Sorry, no. I take it back. No. Well, it has to have to do with a multiplication. Okay, I have. Okay, so now I have A1, A2 equal to 0. I'll multiply these guys. So when I multiply these guys, I'll have the sum of the form minus alpha q squared. And here I have elements, if you want, let me write it as chi r, and R will be running this set f minus v squared. Okay, so this is R, not v. And yeah, it's hard to distinguish between my R and my v. Sorry about this. I'll try to be more careful. So this is chi R. Okay, I'm just multiplying it out. So this is A1, A2. And then there will be chi v. It's plus minus. It's not important. I don't know whether it will be on either alpha v is 0 or alpha v is 1. So either it is in A1 or in A2, but not in both. So I will have simply, and chi v will be absorbed. I understand it now. So chi v will be absorbed because remember, these guys are loops based at v. So if I multiply chi v, but that sum, it will do nothing. Okay, so this is 0 and this is equal to the sum. And now I have these q's running this set, which is not squared. Haha. Oof. So now you see why I wrote it. These guys must, okay, sorry, I should write still alpha q. Alpha q, chi q. Okay, it will be plus or minus. And now this is 0. These guys are basis elements, and you see, if we would assume that here are some edges, right? Then in this set there are no edges. So in other words, that set of chi q's is linearly dependent from the set of chi r's, because R have length at least 2. Remember, they are loops. We already excluded. They are all the loops, so they have length at least 1. Remember, we excluded vertices. Elements in f minus v must be. Well, I don't have to write this minus v anymore because they are loops. They cannot be vertices. So here the length is at least 1 in this set. So when I square it, the length is at least 2. That's a natural gradient. Yeah. Well, we have 2 elements because remember, next to A1 or A2, we have also this chi v. Okay, but chi v will not participate in multiplication by giving us this second summand. This is a result of multiplying by chi v, and the rest is just having that square. Okay, and what I'm telling you is that if here we would have an edge, okay, then alpha q times chi q, where q is an edge, it cannot be annihilated by anything in the other summand, because in the other summand there are no edges. So because of linear dependence, I can conclude that there are simply no edges in this set f minus v. Okay. And now you can guess what I'm trying to do. I will do induction on length. So this was step 1 of the induction. But it's a bit tricky. I had to remember how it's done. I forgot. Is it clear? Is everybody happy? So what I did, with this scribbling here, I justified that sentence. It follows that alpha q is equal 0 for q in f less p. Well, now p is v. That are edges because there are no edges in f minus p squared. Okay, and this is by justification. So that was irrelevant. What was really relevant is the A1 and A2 still multiply to 0. And because all these guys are loops based at V, okay, the KV multiplies by identity. And when I square that set, I have loops of length at least 2. Okay, and we wouldn't have such a cancellation to 0 if there would be any loop which is an edge. Okay. No questions, I understand. So now assume inductively. Okay, now this is very important step. Now assume inductively. Oh my goodness, why did I write it so badly? Inductively that alpha q is equal to 0 for all q in F less P. I mean, P is still V here. That are of length M or shorter. Or shorter. Okay. So you see, the first step of induction is satisfied because we already excluded alpha q's where q is a vertex, and we excluded alpha q where q is an edge. So 0 and 1 are done. Now I assume inductively that indeed all these coefficients vanish if q is a loop of length m or shorter. And now I want to prove that alpha q must be 0 for all q's that are of length m plus 1 or shorter. So this is the induction step. Then alpha q is equal to 0 for all q that are of length m plus 1 or shorter. Well, shorter is obvious because if shorter, then it's of length m or shorter. This is by induction hypothesis. But how about m plus 1? Well, and this is because, so no full stop, this is because the way we multiply. There are no loops of length m. Sorry, there are no loops of length m plus 1. There are no loops of length m plus 1 in f minus v squared. Right? This is obvious. Remember that the shortest loop here is of length m plus 1 because we assumed by inductively that anything shorter is gone. So this means that that the shortest loop in this set is of length 2m plus 2, okay, which is m plus 1 plus m plus 1. And well, and I dare say that 2m plus 2 is always greater than equal than m plus 1. Well, that's simply because m plus 1 is always bigger than 0. M is at least 2, okay? Oh no, so m is at least 1. So indeed, this is true. There are no loops of length m plus 1 in f minus v squared. And the argument is exactly as before. Yeah, if you remember how we argued here, we do this multiplication here. We'll have these two terms. And here we have a problem because if q is of length m is a loop of length m plus 1, but it cannot cancel with anything in the next summand because over there loops are of length at least 2m plus 2. And this way we prove that basically all these alpha q's must be 0. So thus, thus we have shown that A1 is equal to chi v, or A2 is equal to chi v. So I already proved that my sets Pi are non-empty. Whenever I have any vertex V, when chi v, when this vertex V is either in P1 or in P2, that's it. Because chi v is either in the subalgebra A1 or in subalgebra A2. It's not a linear combination of elements. Chi v belongs either to one subalgebra or the other. So that's the magic of path algebras. In general, you wouldn't have it. Okay, everything clear? Because now we're going to return to an arbitrary path. So V will be no longer a vertex. So let us return now to a general finite path P. So we drop the assumption what happens with P equal to V, because we already know what happens with P equal to V. Okay, but I'm sure you agree that then chi P can be written down as chi S of P chi P. These are the relations in path algebra. And therefore, when I look at my unique decomposition, I can write it as chi S of P A1 plus, oh, Hajac, shut up. I don't want an update right now. Okay. Plus chi of SP A2. All right. And now if chi of SP is in A1, then A2 is equal to 0. Why? Because I know that, well, I can write it down like this. Because of the uniqueness of a decomposition, A2 is chi of SP times A2. But if, remember that this is a direct sum algebra, so A1 times A2 is 0. If this is in A1 and this is by assumption in A2, then they multiply to 0. Okay. And of course, vice versa. If chi of SP is in A2, then A1 is equal to 0. Right, and likewise, if chi of SP is in A2, then A1 by the same argument is equal to 0. But in any case, alpha Q is equal to 0 for all Q that are not P. And alpha P is equal to, sorry, I wrote chi and I meant alpha. And alpha P is 0 or alpha P is 1. So now we can conclude that chi P is in A1 or chi P is in A2. Well, why can we do it? Let me think. Why did I write this sentence? Well, of course, remember that we have this decomposition at the very beginning. You see this one at the top of the board. And when one of them is 0, and remember, one of them must be 0. This is what we just established. Either A1 is 0 or A2 is 0. There is no other option. Well, when A1 is 0, then I have always alpha Q equal to 0 and alpha P equal to 0. If A2 is 0, well, I have minus alpha Q equal to 0, but I hope you agree that minus alpha Q equal to 0 is the same as alpha Q equal to 0 in any field. And then we have 1 minus alpha P equal to 0. It means alpha P equal to 1. Okay. So we have either A1 equals chi P or A2 equals chi P. That's it. So chi P is either in A1 or A2. And this is exactly what we wanted to prove. So now it's down the hill. We have climbed the top. Now it's just down the hill. This was the toughest part of the argument. And now I can draw my conclusions. Okay. So consequently, not only my sets Pi not empty, but my space of all finite paths decomposes into the disjoint union of P1 and P2. So of course they intersect to 0 because A1 with A2 intersects to 0. And so this means that the intersection of P1 and P2 is an empty set, because if I have a path, then chi P, and have a path P, then chi P is never 0 because the basis element. Okay, so it cannot be both in A1 and A2 because the section A1 and 2 is 0. So the intersection of these two sets is by construction 0. It was clear from the beginning. But now what we just proved is that we take any path P and then chi P is either in A1 or in N2, which means that P, our finite path P, is either in P1 or in P2. So I have this beautiful decomposition. Okay, this is exactly what I wanted to accomplish. All right. We still have one argument to construct the graphs U1 and U2. Okay. So we have just shown that we have this decomposition of FPE into disjoint, and of course these P1 and P2 are non-empty, so maybe I should still write it down, that they are non-empty. So let me do the following. I erase this argument, and I'll write down that P1 is not empty and P2 is not empty. Right, because well, assume that all chi P's are in one of these two subalgebras, okay? But then it means that the whole path algebra, which is a linear span of all chi P's, is equal to the subalgebra. So we have one as 0. It contradicts our assumption. So these sets must be non-empty, both of them. This is exactly as we wanted, the decomposition of all paths into two disjoint non-empty subsets. Okay, and now I'm going to do the following definition. This is important. I define EJI as EJ intersect PI, where I just equals 1, 2, and J equals 0, 1. So you see, this is why I used superscripts for telling whether I mean vertices or edges. Okay. So since I decomposed all finite paths into P1 union P2, I can also decompose edges and vertices. And this is exactly what I'm doing. Okay. And then I can define my subgraph EI to be what? Well, it's EI0, E1, 0, sorry, E0I, E1I, SI, TI. Of course, I is all the time 1 or 2. Well, these are subgraphs. Okay, is a subgraph of E. Is a subgraph of E. For the appropriate restrictions, SI and TI of S and T, respectively. Well, and this is not obvious, but I have an argument here, and this is because, and let me understand my own argument, because ISE chi E equals chi E equals chi E chi TE. That's definitely true for any edge E. And A1, A2 is 0. I just mindlessly copied it from the notes, and that's why see why is it true. Why I can surely define such subgraphs. Well, I can surely define such subsets EJI, no problem. Okay. And now, why are they subgraphs? So I must make sure that if I restrict myself to an edge, which is say in E1, and I apply the source or target map, I will land in E0, which is in the same subgraph. So, okay, let's take SSI, and how does it help this equality? Okay, yes, it's obvious. You see, yeah, this is funny in mathematics. I mean, you look at something and it looks like impossible, and in a second it's obvious. It's indeed. Imagine that it happens that I have an edge E, which is say in E1, and I apply the source map. And imagine that the source map is a vertex which is now in E2. It must be in E1 or E2, there is no other way, okay? But if it is in E2, then chi SE is in A2, and chi E is in A1, so it must multiply to 0, which is impossible because chi E is a basis element, okay? And the same for targets. So this innocuous obvious equality, or two equalities, force the restrictions to give us subgraphs. Okay, if I restrict the source map to E1I, then its image will be in E0I for I equal 1, 2, and the same with targets. Okay, so they are indeed subgraphs. Okay, so now I have subgraphs. Yes. Now by construction, they are these joint subgraphs, but it gives us the whole graph. Yes, of course, because remember that the intersection of P1 and P2 is empty. So intersection of any subset of P1 and P2 is also empty, and the set of edges and the set of vertices are by definition subsets of Pi, okay? So you have it by construction, and also by construction, we have that E is the union of these two graphs, because every edge is either in E1, or in E1, 2. It must belong somewhere. It's either in P1 or in P2. So it will be either in E1, or in E1, 2. The same for vertices. Okay. And of course, you know, because the intersection is empty, the intersection exists and the union exists. Remember that previous semester? Okay, so now I also have to argue that they are non-empty. And this is the last part of the argument of one-way implication. But by the way, I also want to prove that A1 is K of E1 and A2 is K of E2. And then we'll have that they are non-empty because the path algebra of an empty graph is 0, and A1 and A2 by assumption are non-zero. So let's do two things in one go. So this is the final argument for finishing the one-way implication. Okay. So finally, as E1 non-empty and E2, this is empty, looks so strange. And E2 non-empty follows from K E1 equal A1 non-zero and A2 equal K E2, A2 non-zero. It suffices to show that K of EI is equal to AI, and as always, I equal 1, 2. Okay. So then we'll show that this E decomposes into this joint union of non-empty subgraphs. And moreover, we have it in our theorem that in fact A1 is equal to KE1 and A2 is equal to KE2. So let's do it. So first observe that KEI is in AI by construction. Right, because what do I do? I have edges and vertices which are in, say, Pi, and I construct paths out of them, okay? And then they will all be in AI. Why? Okay, so somehow we have to use this fact that these guys are disconnected. Okay, so we have that FPE is equal to FP1 union FPE2, and well, disjoint union. So that will be easier. Because imagine otherwise, imagine that you have a path which is neither in E1 graph, subgraph, nor in E2, okay? But then it means that we would have to have one edge or one vertex from E1 and one edge and one vertex which are adjacent to each other in E2. But this would contradict the disconnectedness of a graph. Yeah, if I have, say, an edge or a vertex from E1, and here an edge or a vertex from E2, and they meet here, then of course this vertex must belong to the graph E1, and this vertex must belong to the graph E2, which means it belongs to the intersection, which is empty. Okay, so there are no paths that mix vertices and edges from different subgraphs. Okay. So my path is only in E1 or only in E2. Okay, sorry, I was stuck for a while, but it's obvious. Remember that AIs are ideals. Okay, so I think this was a bit roundabout. Of course, I know by definition that all edges and vertices are in AI. That's by construction of a graph EI. But I want to have all finite paths in AI, meaning the characteristic functions. And I know it because it's an idea. Whichever path I will take in EI, it must have a vertex which is in AI. And because it's an ideal, such a path must be in AI. Okay. So this is obvious. I'm sorry. This was true what I said, but redundant. It's really obvious by construction. Maybe I'll write here AIs are ideals. Okay. Now it's a bit more tricky to prove the other inclusion. Okay. So now suppose that we have an element A which belongs to AI less KEI. Okay. Then, well, I can write it as follows. Let me do it on the next slide, because there is not enough room here. Because I have a basis, I can write it down as a finite linear combination. So I write it as a sum over paths P that run some subset Fi of Pi. Here I have my coefficients alpha P, chi P. And now it is plus sum over Q running another set. Let me call it Fj, which is now a subset of Pj. And I have alpha Q chi Q. Right, I'm just using the fact that chi P's give me a basis where P run the disjoint union of P1 plus P2. Disjoint union of P1 with P2. Okay, so I have these two summands in a linear decomposition of a in terms of basis elements. Okay, and of course Fi and Fj are disjoint because Pi, P1 and P2 are disjoint. So F1. Well, I should write it down. Sorry, I should have finished first. So I is different than J, and of course Ij is 1 or 2. Okay, and remember Fi intersect Fj is empty. Okay, and is empty, and they are finite. So right, because it's a basis in a normal algebraic sense. So an element is a finite linear combination of basis elements. And we can assume without the loss of generality that all coefficients are non-zero. So all alphas are non-zero and all coefficients are non-zero. I mean, otherwise we just dump it, okay? If I have some basis elements such that the coefficient next to this basis element is 0, I just remove it from my set over which I summed. Okay? And we know that A can be always decomposed into the sum of such two sums. However, then we get the desired contradiction. Why? Then we note that A minus sum over P, this is the same as above, I'm just rewriting it. This is not 0 and it's equal to the other guy, so sum over Q in Fj in Pj alpha Q chi Q. Well, why is it not 0? Well, because we assumed that A is not in KEI, all right? So this means that this cannot be a linear combination of elements from KEI, right? This element is in KEI. So if it were 0, I would be in KEI, which we assumed it is not. Okay, so then this is a non-zero element, but of course this is equal to the other sum, which is entirely in K EJ. But better still, what I can say, well, we assumed that A is not in KEI, but we assumed it is in AI. So this first term here, the difference of two elements, this is in AI by assumption, because KEI is contained in AI. A is by assumption in AI, and the other one is in KEJ, which is of course a subset of AJ. So this is an element of the intersection, which is 0. So we have a contradiction. So, which is the desired contradiction. Okay. So I hope it's clear, because this is in KEI, but A is not in KEI, so this is not 0. But the whole thing is an element in AI. This is an element in AJ. So this is an element of intersection. So we have that something is simultaneously 0 and not 0. This hardly ever happens in an algebra. Of course, we must have a 0 algebra, might have a 0 algebra, but this is not a 0 algebra by assumption. Okay. I think I mumbled something nonsensical. Anyway, I cannot have an element which is simultaneously equal to 0 and different from 0. Sorry, forget that. I don't know what got into. Sorry. All right, we are done. We are done. We proved the first implication. Okay. This is so much better than writing on a blackboard, because now I can just go back to my theorem and point for you what I have in mind. You see, so we proved that if our path algebra KE decomposes into a direct sum of non-zero subalgebras, okay, then we can decompose our graph into non-empty disjoint subgraphs, and moreover, which is important for applications, we have that A1 is equal to K of E1 and A2 is equal to K of E2, okay? So now the easy peasy part of proving the implication the other way around, which is just, why is this page 10 empty? Somehow skipped it. I didn't do it on purpose. I have nothing against number 10. It's Downing Street number 10, for instance. Okay, so now to end the proof. Oh my goodness. And again, but okay, this is really the end of the proof. I should do it within 3 minutes. Again, I overdid it. To end the proof, let us show the opposite application, implication. Let us show the opposite implication. So we have a decomposition, this is by assumption now, into disjoint non-empty subgraphs. Okay. But then it's clear that we have what? First, it's obvious that K E1 is not 0 and K E2 is not 0 because E1 and E2 are non-empty graphs. And now we can conclude that KE is just the direct sum of these subalgebras KE1, KE2, because, and now this is an important argument, because FPE, so luckily I already argued for it, okay? I already argued for you that FPE is just FP of E1 union FP of E2. There can be no paths that mix edges, vertices from one subgraph of another. We already argued about it. So FPE is the union FPE1 and FPE2. Okay. And by construction, we have that FPE1 intersects with FPE2 to the empty set. Right, you cannot have a path which is simultaneously in E1 and in E2 because they are disjoint subgraphs. Okay, if you have any path which is simultaneously in one graph and another, then it's a beginning would have to be in both graphs, and then we would have a non-empty intersection of a set of vertices, which is impossible. And then this follows because you have the spanning property from the first statement. So because all finite paths are either finite paths in E1 or in E2, then it's obvious that KE is equal to KE1 plus, not O plus just the usual sum of KE1 and KE2, the spanning property. And the fact that these two subalgebras intersect to 0, it comes from the second property, right? Because the basis comes in from FP1 for E1, FPE1 for KE1, and the basis is FPE of E2 for KE2. So because the basis sets intersect to the empty set, then indeed the intersection of these two algebras is 0. And finally, do we multiply component-wise? Yes, because if I take any chi p with p in E1, with p in FPE1 times chi q in FPE2, this is 0 for any p in FPE1 and q in FPE2. Right, because this is always 0 unless P and Q forms a path. If P and Q forms a path, then the end of P is the beginning of Q. But this means this vertex is both in E1 and E2, which is impossible. Okay, so this ends the proof. I like this theorem very much. Let me just mention that there is a similar theorem in this blue book about representational theory and path algebras. And but our theorem is much stronger. So for starters, we do not assume the unitality. They do it under the assumption that KE is a unital path algebra, which means that the set of vertices is finite. This is completely redundant. When your algebra is unital, then this decomposition direct sum means the existence of non-trivial central idempotence. And they argue this way, but this is completely redundant. You don't have to do it. Our proof is, believe me, not more complicated than theirs and much more powerful because we handle the non-unital case just as well. So this is one win. And the second, and we also don't involve additional concepts like central non-trivial idempotence. We do argue directly. So this is win-win. And the third win, I would say, is that we say a little bit more. We don't just conclude then the graph is disconnected. We actually say that A1 is the path algebra of one graph, subgraph, and A2 is the path algebra of another subgraph. And we will use it next week. So sorry again for extending. Let's meet at 11:45 for the recitation class. I stop recording.